Good afternoon, everybody. We are the Marquette University Solar Analysis Team, and our district use case is the City of Denver / Auraria Higher Education Center. We approach this project in a problem statement, which is to design a solar and battery storage installation to drive Denver and the Auraria Higher Education Center towards sustainability goals of carbon neutrality by 2050.
I'm Nicholas Fuentius. I'm the conceptual system designer.
I am Eric Helm, and I was the distribution system impact analyst.
I'm Adam Pink, the development planner.
And I'm Konstantinos Kopoulos, the financial analyzer.
Right, so our plan is to design and create the most optimal solar PV and battery backup system for the city of Denver and the Auraria Higher Education Center. We'll be exhibiting our plan to install a solar PV system on the roofs of buildings to offset the daily usage of the schools and city, while also introducing some integrated structures for students and public use. We will be looking at 5 buildings total that are split down the boulevard, with the Auraria side on the left. There will be 3 buildings and 2 buildings on the right on the Denver side. For our solar panel analysis, we went with an LG Neon 2 series solar panel. We chose this brand as LG is one of the leading manufacturers in solar panel productions, and the Neon 2 series is highly regarded and trusted by those who have used the model. Our criteria for the solar panel was that it had to be reliable, it had to have a good module efficiency, and it had to be able to withstand the harsh conditions of Denver as they receive a lot of snowfall. And moving on, our criteria for the buildings to host our solar panels was that they had to have a lot of space on the roof, and secondly, they couldn't be shadowed by any other surrounding buildings or objects. So to start, we're looking at the west and south classroom on the Auraria side. This was an easy choice for us, as it already had a solar panel array built on the north side of it, I believe, and there was much room left that we could utilize for the roof. And then next is the Cherry Creek building. That, as you can see, it's a relatively simple flat top rooftop with a plethora of space. And as you can see from the panel alignment placement, we plan to utilize just about all of it. And then lastly, we have the science building, which quickly became a priority for us as we discovered early on that the science building uses the most power of all the buildings whose data we had been provided of. And we wanted to ensure it got proper attention and a strong solar array. And then moving across the boulevard to the Denver side, we have the convention center. And as per the guidelines to the top left of the convention center is not to be used as it is undergoing renovations. However, it still makes it by far the largest structure. And as such, we wanted to take advantage of the space and really milk the solar panel potential for all it had. And then finally, we have the theater complex building, specifically the Helen Bonfils Theater, which is a flat top roof that neighbors the convention center. And then here we kind of have the estimated output of each building, assuming normal working test conditions every day for year round with an average of 4.87 hours of peak sunlight the panels would receive a day. And then here we have, we'll showcase a collaboration we had undertaken with 2 students from the Milwaukee School of Art and Design. We had an idea after reflecting on the mission to move towards renewable energy. So we had these 2 students design some potential ways to show off the push to renewable energy in hopes of perhaps modernizing the campus a little. This first showcase is a concept for like a solar canopy that could be used over the large parking space that is on the Auraria side. This design would work to provide additional solar power generation, as well as cover the parking lot cars from harsh weather conditions. Additionally, on the next slide, we had them develop some smaller scale designs to utilize solar panels to make for an outdoor common area where students can hang out, meet, and perhaps work on homework.
And that will bring us to the distribution system impact analysis deliverable. And the goal for this section was to use our plan from the conceptual system analysis to develop the power flow that would work for the system, while gaining the understanding of how the power is flowing through each individual system as it is right now. For us, the most important aspects of this was to make sure that we had the correct PV system specifications, as well as implement the climatic and efficiency data in and on each individual system. So the main new addition to our project since the progress deliverable was the implementation of a battery storage unit. And for this, we chose to use the Tesla Powerall 2. Our thought process behind this choice was similar to with our choice for solar panels, in that we wanted a reliable distributor so that we could eliminate some risk of the equipment malfunctioning and causing error and increasing costs. We ran the test to make sure that it would be reliable in the case of a blackout and that it would store enough energy to be cost efficient, as the pricing was also very important for us when making this decision. For our power flow model, we chose to mainly use OpenDSS as much as possible because we felt it gave us the most freedom to analyze the baseline case and make the adjustments gradually as we went along throughout the project. So we pretty much observe how each change we made to our project and our proposal would affect the distribution system. And we could see gradually along the way if there were any changes that we needed to be made or adjustments. And then the distribution system risks, the most important ones that I guess we faced throughout this process was overvoltage, which would come from too big of a PV system or they're too close together. And we were definitely looking at a lot of that. And we also make sure that the battery storage would be able to support this PV system and help out so that we could avoid overloading the voltage.
After analyzing our risks, we decided to analyze our costs for solar utilizing NREL sources, extrapolating the curve to the right to better accommodate our larger installation. In our simulations, we analyzed Auraria as a large array made up of multiple subarrays on each rooftop, interconnected into the science buildings, battery, and solar ecosystem. For Denver, we decided to sell solar renewable energy credits, or SRECs, which is 1 SREC per 1,000 kilowatt hours. Looking towards battery costs, we also utilized NREL sources since we are installing 0.5 megawatt hours capacity in Auraria, which would give us an average of 4-hour resiliency, which is twice the average blackout in the US of 2 hours. In our simulations, we utilized the batteries in 1-day look-ahead peak shaving. For our economic inputs, it can be seen that Auroria's cost per watt is 2 cents higher than Denver. This is because for Auraria, we are installing batteries and solar, whereas for Denver, we are just utilizing photovoltaic panels. The operations and maintenance is also higher for Denver than Auraria, which is because we are utilizing more material there, which has to be maintained. And our SREC price after researching came out to about $200 per SREC. Moving forward, those inputs give us a number of outputs. It can be seen that the construction loan amount is higher for Denver than Auraria. We also took into account the line build to the intersection from the Denver Community Solar into the construction loan amount. The results of our simulations gave us double the P50 production for the Denver Community Solar than Auraria, giving us over 8,000 SRECs in the first year alone, which led us to a project IRR of 20.14%. For Auraria, the value of electricity savings increases exponentially after the first year of installation, which is $163,000 saved, followed by the after-tax cash flow, which turns cash flow positive after the 20-year mark.
The development plan essentially seeks to satisfy all requirements and expectations of master plans for both the Denver and Auraria campus side of our district. The development plan also covers all zoning codes and permits required in the installation and the timeline of installation of our proposed project. The most significant plan that we are working around, as Nick mentioned earlier, regarding the Denver side, is the renovations on top of the convention center, essentially avoiding the 25%, roughly 25% of the roof on the convention center for installation of our solar panels. One thing that we've also identified is there is a green roof ordinance in the city of Denver, essentially stating that any new or renovated roofs above a certain square footage require that a building incorporate carbon offset technologies, whether that be green roofs or solar panels. So for the renovation on the convention center, our solar panels would sufficiently meet this requirement, as well as for any other buildings in our district. On the Auraria side, courtesy of the Auraria Sustainable Campus Program documentation, we looked at the 2018 solar PV roadmap, which essentially outlined their priority list for buildings to have solar installed on them. Since the publication in 2018, a few of these buildings have had solar installations included on them, namely the arts and library buildings that were recognized as high priority in this roadmap. So going forward, we made sure that we were still choosing buildings that met high priority line items for the campus, and also had sufficient roof sizes to meet the goals that we had for power production. In terms of permits and codes, in installing our proposed project, we would need to obtain contractor's licenses, zoning permits, which are required for any installation that includes angle-mounted panels and or batteries. We would also need to file for building logs and electrical permits. Some of that documentation is behind the IRC M2301 and IECC 2018 documentation, though some of these documents are behind paywalls and would require that we are legitimately applying for these licenses. In terms of risk analysis, I have a few examples of risks that we analyzed, though it's an abbreviated list. The biggest mitigating efforts that we employed were using components from reliable manufacturers and reliable components themselves, as well as budgeting sufficient time in our timeline for any unexpected delays, and structuring that timeline such that we would be able to adjust things on the fly. And here is the development timeline that we have worked out. As you can see, the procurement and installation processes are the longest in duration. And this is based off of estimates in working with an industry advisor and identifying strains on the supply chain currently, as well as construction protocols in place due to COVID-19 restrictions. So in the case that some of these stresses and restrictions are alleviated by the time of implementing such a project, some of these sections could reasonably be shorter and our project would be completed sooner.
So how does all this align with the district and the competition's goals? Well, all of our installations would offset 4,814 metric tons of carbon dioxide per year, which moves Auraria closer to carbon neutrality by 2050. These installations, as well as our My Identity Life solar project collaboration, would also promote sustainability and energy in everyday life. These projects are also economically viable, with Denver having a 20% IRR and the Auraria installation paying itself off in 14.7 years based off of our installations alone. As well as the Auraria campus having a battery backup of 4 hours on average for the science building to prevent any loss of experimental data as well. These are our references. Thank you everybody for your time. And does anybody have any questions?